to find good key points is a corner detector. And that's just using that the edge detector that I mentioned earlier. It'll find edges, horizontally and vertically, and just seeing, hey, are these different edges, are they strong in the same spot? And we've got this image here. And you're like, oh, that looks like a corner because it changes a lot vertically and it changes a lot horizontally. So then it becomes the corner in the plot. And it says like, okay, these are points that are, that will be easy to pick out. And once we pick out those points, we have to describe them somehow. Because, going back to this image, how can you tell these two corners apart? There's no way to do that if you're just saying what corners are worth looking at. So in this example, there's a descriptor. So once we've decided these points are worth looking at, we're going to describe them. We're going to say what's around them so we can match them. And one of the ways to do that is called SIFT. And there's like 7, 20, 200, 1,000. There's very many ways of describing these points. They all have fancy names, but one of the first is SIFT. And it uses those edge filters and those gradients and those frequencies that I talked about earlier to describe what's going on around the key point. So it's saying like, all right, so to the bottom left, there's this certain feature. Maybe it's like low frequency and it's like red, just very red. And so it describes each of those corners in that way. So then we have not only, hey, these points are important, but I can describe what's around them. And so bringing it back to that whole problem of drowning in data, we've just turned this big image into a few key points and a few descriptors. Then we don't have this problem of, oh, I'm just dealing with loads and loads of data. It's now significantly smaller, orders of magnitude. Questions at this point, because I'm seeing in particular a few confused faces. Go ahead. Okay. Okay. Peter, how much time do you have? Yeah, so the question was, when you're, so if I understand you correctly, when you're figuring out how to describe these points, you might have to translate a lot. So like, in the previous image, if I step to the back, this book is oriented this certain way, and it's completely different. It's not completely different. It's mostly different in there. So like, how do you deal with that like rotation without brute forcing? Is that? So actually, the angling is less of a problem in practice, because you can either get a lot of photos of something in different orientations, more work, but you generally get better results. Also, the descriptors usually turn out better if they have some sort of resilience to angling away. So it's not in particular, I could go in the details about that, I probably will in Hackerspace. But in practice it turns out not to be that bad. However, with rotation, there's actually a quick and easy way to orient them all the right way. So using that edge detector filter, you can tell the key point what direction is the strongest, what direction has the strongest gradient. Then you spin all the key points to point, so the strongest gradient is up and down. So then you have this invariant, this order to all the key points, and you can match them up. Sometimes it doesn't work out, but that's why there's lots and lots of key points. It's like sometimes this matches that, that's not a match. but you get a lot that are right. And I'll go into, in Hackerspace, how you can take all these matches and get one that works well. Descriptions. All right, what can you do with it? I just talked about why computer vision is worth looking at, what it is, some methods of getting started with it. Now, what can you do with it? Why is it worth studying? So this image has been floating around in computer science land for a little bit. This is from Google's Deep Dream. And Deep Dream is a neural network that Google engineers created that will take images in and describe them in some way. So, it was trained on a bunch of images. So this would say like, oh, this region's a tree, this is sky, this is ground, this is an ibex. I don't know. Let's see. Alright. I don't know what that animal is in particular. But the way it did that was many layers of neural networks. And you heard about neural networks with Shotaro and Jordan. But the beginning layers of the neural network start out in the same way that the edge filters and frequency filters do. So you can start to see, oh, here's a lot of lines. And this image on the right is something that the Google engineers took. They took the results from this algorithm and said, oh, this is what the algorithm sees in this image. And it accentuates that. So it takes the image and then overlays. This is, in a sense, what the algorithm sees in the image. And when it's trained on different things, for example, buildings or dogs or people, just the general images that were put in the algorithm, you can put an image, ask what the algorithm sees in it, and expand on it. So they stuck this through the process. And it took this image, looks like a desert with tree, rocks, and it added in a lot of detail that it thought it saw. So you can see there's like rooms and buildings and arches and a lot of people walking around, and like a dog face over here. And it's pretty cool seeing, oh, I guess there is this sort of triangular feature here that gets turned into a bunch of arches. So this code is actually on GitHub. You can put your own images into it and start playing with it yourself. So we promised something fun. If you remember, Modi and Connie at the VRL lecture asked you guys to take a photo and send it to us. Sadly, we didn't have enough photos to reconstruct a Siebel well. We got like 13, which isn't a lot. But we got a different reconstruction. We took a tablet called Tango, which is currently in development phases. But the idea is it takes this video feed that it gets, along with the motion sensing that like a normal tablet or phone would have, in creating a 3D model. So this was, when we walked around with it, I assume it was late one night, and just walked through Siebel and got a 3D model of it. So as you can see, it's fuzzy. But it's a 3D model, and that's enough that if I were to take a photo, I would be able to place this photo where it was taken in this model. So I thought that was really, really cool. That stuff we have right now, you can walk around with a tablet and it'll reconstruct. All right. So I'm wrapping up. We've heard why computer vision is worth looking at. What makes it cool? How does it work? A little bit, broad strokes. What can you do with it? Now, what do you do now? Perhaps, I really hope that this interests you in some way, shape, or form. I first started looking at computer vision for my CS196 project back when this was a very small and quiet class. It was far too ambitious. I'm still working on it now. But it's a lot of fun. I'd like to finish it up soon. And, nobody goes around and tell me like, hey, how do I start looking into things? How do I start playing around with computer vision, learning? So, last slide, that's what I'm here to tell you about. So, as you may have guessed, there's a lot of linear algebra, there's a lot of matrices in computer vision. There's also probability, because things get fuzzy. You have strange data. Data that may or may not be reliable. Machine learning, like I said, one way to think about computer vision is just machine learning with images. And then two more classes that go 400 levels, but computational photography, which is like Photoshop with more math. And we learned a lot about vision and just the computer vision class itself, which I will be taking next semester. Then for projects and tools that you can start working with. Like I mentioned, there's Google Deep Dream. That code is now available on GitHub. Google's very nice about that. You can start putting in your own images and training it, seeing what strange dreams it comes up with. Bundler, which was one of the tools that we were planning to use in reconstructing 1404, where we didn't have enough pictures. Then also OpenCV. And OpenCV is the Swiss Army knife of computer vision. So if you're looking for an edge filter, if you're looking for the feature detector that I was talking about, if you're looking into recomposing things in 3D and you want to do it in code as opposed to just running a program on a computer, you should definitely look at OpenCV. Lastly, lots of credits. There comes CS445, computational photography, a few icons, and Google Deep Dream, and the stuff from Tango. So, yeah, I hope you're excited, and see what you guys can do.
All right, so we're going to be having a couple more team presentations right now. So first up is Workout Buddies, and on deck is Extensible RPG. So if Workout Buddies could please come down.
You gotta see what they've done. I'm sure they're great. Jennifer sure is
Hi. Okay, so we're Workout Buddies, and we're just trying to make an app where if you want to, you're trying to be a healthier person or maintain your lifestyle and fitness goals, so you can find someone that's like the same gender, age, body type, fitness level, so stuff like that can go work out with you. So right now, what we have at least like the user profile part, and then we're gonna have it do where you put in what preferences you would like for the different levels, and then you get a bunch of other people that are on the app that put down those same thing. So, and then you can contact them. But yeah, so first we're going to show you like our little account, and then later we're going to show you like how you can do the preferences. And yeah, so right now it's kind of on 2 computers because we were like doing them separately. But that'll be the next step, probably just like mashing them together and then making it prettier for sure.
So this is the interface where you can create a new account. That means when you first open the app, you're gonna to create a new account. That's where you do that. The first thing is username. Like you can put whatever you want, and password, first name, last name, email. Yeah, cool. And your mobile number, which have to be 10 digits, or it will send you an error. And your age group, choose which age group you are in. Like this, and gender, neutral. Fitness plan. Basically, we now have three types of fitness plan. That is weight loss, muscle gain, maintenance. Let's just choose muscle gain. And fitness level, let's choose beginner. Gym frequency, you can see 1 or 2 days per week, 3 or 4 days per week, 5 to 7 days per week. Let's just do this. Availability, that's when you want to go to the gym. So just randomly choose one. And the photo thing is, we haven't done that very well, so it's just, you can see it, but we now can't do anything about it. Now we can submit. So new account will be created in our parse database, which later you can see. And if now I cancel this, you can see a map thing, which is zero, because I haven't given it any data. If now I give it a data, give it some data. This is the latitude and longitude of Sydney. Just send it, and you can see all the gyms around this place. Basically, it's 5 kilometers radius. All the gyms are in this map, so you can choose which gym you want to go later in this app, but now not. Okay, thank you.
Okay, so we right now have this like little preference maker, so you can just pick random stuff. It's doing so well now. And then if you click that, it'll kind of like, these are just random accounts we made when we were just putting in fake data, but yeah, it'll like bring back names and stuff, and soon we'll have like the rest of the data.
Yeah, the names are in the parse database, that's what we said.
Yeah. So yeah, cool.
All right. Could Extensible RPG please come down? And next on deck is what to wear.
Let's go.
You could turn the jump.
Okay, hello. So we're the Extensible RPG project, and so basically what we're trying to do is build an RPG, and while we build an RPG, also sort of build the engine for it and make it so users can modify the engine and like the mechanics of the game and like pretty much anything that they want to modify. And so yeah, that's pretty much what we're doing.
Alright, so kind of an important component of our RPG was like random maps. So I made a like random map generator that basically like takes a couple noise maps and then samples that, and then based on like it basically generates values for altitude and moisture, and then we take like those samples and then assign them to biomes. So you get this kind of like natural looking terrain.
I don't know if it like launched or anything.
Yeah, so like each time you generate it, it looks slightly similar, but it should be different each time. Oh yeah, go back.
Okay, so now I guess we'll show you guys like our debug version of the game itself.
So,
Here, right now. So you can like select a character, and then so this is an NPC that's like friendly and will follow you around, and then there's like this random dude walking over here, and then there's a trader, and you can like click on him, and sorry the screen is too small, so it's like off the screen, but you can trade. And then you can also craft things, and you can like move stuff around in your inventory. And then we have like a little building over here. Oh yeah, and your character is naked right now because you don't have anything equipped, but
this one.
-2.
and so yeah, and like our biggest problems were probably the first challenge that we had to like overcome is like first procedurally generating a map, and then after you procedurally generate it, like how do you store the data, and how do you like take the data and like put it on the screen and load it so it isn't like really slow. And so that was like a huge challenge that we faced because like we aren't using Unity or like other game engines. Like we're actually writing the game engine ourselves, so we have to like solve every problem. We can't like relegate anything to like someone else. And yeah, and so I worked on like basically loading the map, and like Ben worked on making it and like various parts of the GUI, and Sean worked on like NPCs and stuff, and then Hansong was helping us with like basically like quad trees and things like that. But it's I guess like that's pretty much our project.
Where do you want
Yeah. Yeah, and so then also like, sorry, we're not done yet. In addition to the game, we're also building like an editor. Oh.
Wait. There's an easier way to do this. Like, keywords and stuff. It's
I've already heard that. No, I've pretty much already done that. Okay. What the fuck?
So, oops. So, this is like the editor right now. It's like really, really basic. Basically, you can just like move around the map, and then you have your like tool tray, and you can like select a different tool and edit the map, but you can't actually do that yet. So yeah, that's pretty much it.
All right, could what to wear please come down, and next on deck is open source story writing.
Okay,
show me website and I'll
okay, let's reply to this. You're right.
We are what to wear.
All right, so we're going to start this a little differently than other groups. I want you to take out your cell phone. Take it out. Open your Messenger app. Open it up. And you're going to text my phone number, which is 331. Actually, I don't remember the phone number. There it is. It's 331-305-6064. 331-305-6064. Don't text it yet, though. All right, so what you're going to do is you're going to text it your zip code with your home address. And then what we do is we take that zip code, we get the weather, and we tell you what to wear based on that zip code. Or if someone doesn't type in a zip code and it crashes the server. That's also possible. So you should all be getting text message responses until someone doesn't type in the right thing, and then it crashes the server. But we're just going to put it back up. So that's one component of our app, is text messaging. So now, does anyone else want to talk about the other components?
So it is also possible to get access to our service via our website. And here we can sign in, but actually I'm gonna sign up first.
Just wait a second.
Okay, so before we talk about website, we are going to show you like our Android interface. Like that's it. So that's how we get started. But we still haven't like finished all of them. So that's also part of our program because we want everyone to be able to use it on their phone. Yes.
Okay, so back to the website. So we have a lot of the like UI implemented, and recently, as of about an hour ago, we have some functionality too. So now if you click sign up, it takes you to the sign up page, and it asks you for your username. So what's our username? We'll type in Peter, and then we have a phone number 888-886-3345. And we have his password, and we'll make it I'm cool. And gender, male, submit. So now nothing happened here. You don't actually think anything happened, but the reality is that if we were to take a look at our database over here. Over here. We can do db.documents.find. And there we go. We have Peter at the bottom here with his gender, which is female actually, and phone number and password, which I guess didn't go through. But we have some data storage implemented. We have some of the website functionality implemented, and the Android app and text messaging.
I mean, another cool thing is someone else can hold this so I can show my wrist. Alright, thanks. Just basically with the whole like app and the texting thing, look, you can do it with the watch too. See, if I reply to that same number with the zip code for Champaign, right here, you can see I got a message, and it tells me what I got, and look, it tells me what to wear.
And that is all.
Thank you very much.
All right, cool. So can open source story writing please come down? And next up is visual novel.
Yeah, I just changed that. He was in there. There's 2 of them to come in.
Alright, so we are open source story writing, and basically we are creating a website that allows you to write stories and have an interactive writing experience, similar to the way GitHub works and source control. So what we have currently right now is a basic website that shows you stories that are published, either published, in progress, or popular. And we don't have too much interaction right now because we haven't connected our back end to our front end yet. But what we're hoping to do is allow the user to see other stories that are in progress and basically fork them and make edits of their own and merge them back in the way our source control works. So.
Yes. This is the general layout of the website. We have different tabs for different types of stories. So, like, ideally, we'd have the front page be all of, like, the published and like finished stories, and the second tab would be kind of the stories that are in progress and people are still kind of editing, and those are kind of the stories that people are working on. And then we just have another tab that would be popular stories. And then we have like different categories in the search bar.
Alright, can visual novel please come down for the last presentation? Wait, are you? You guys are on deck, by the way.
Hi, hi. We are Visual Novel Group, and for this project, we are building an engine for developers to create visual novel, and basically, you can use our engine and write your script in Lua code, and our engine will read the code and render the pictures according to your script and build a game for you. As you can see, first we have the login interface. We have first account is your email and you have password.
Yep, so it actually works. So, for example, I'm going to make a new account here. It's called bob@gmail.com. And then you can set a password, so I'll put ABC. You can register, and it will create your account for you. And you can log in and log out. And what this thing does is that you can sync your settings and your game progress across your devices. So let's get started with this demo, shall we? So yes, as you can see, we are very talented artists. But so yes, so my name is Bob, and I am a stickman. As you can see, my creator was an incredibly talented artist. But anyways, so here's a couple of the features that we implemented. So as like just now, you saw him like move in from the like outside of the screen. You can do rotation. You can do scaling, and you can do transparency as well. So yeah. So you can have multiple characters. And so yeah. So our engine runs on Windows, Mac OS X, Linux, Android, and technically iOS support, but it has not been tested since nobody here has a Mac, but it should work in theory. And so yeah, you can sync your data across devices. So I'm going to demo this right now. I'm going to press save right here, and it's now saved. So if I hop over to my phone here, okay. Yeah. Don't judge me. Okay. Alright, and we're going to log in with the account that we just created. Sorry about that. Okay, so as you can see, we logged in to, sorry. It's not showing. We are currently experiencing technical difficulties. Sorry. Let's restart this. Alright, so anyways, yeah, okay, there we go, we logged in. And this is the same account that we just created, so we can now resume it on our phone. As you can see, we are at okay. Okay, so yeah, as you can see, we are on the, this is the same frame that we were on our computer. So we can also, let's progress and save it on our phone. And we can go back to our computer and we can resume it. And so yeah, it's now on our computer. And so, sorry. So yeah, and the games are written in Lua. That is completely wrong, and let's go show how easy it is to change that. So we're gonna go and exit this, and go into our folder. Oh, okay. Well, anyways, it's really easy to edit your game. You can just open a text editor, and you don't have to recompile any code. And you can just directly send that file to your phone. And yeah, so thanks.
All right, can EKey please come down?
All right, so let me see just a quick raise of hands. How many of you have forgotten your keys at some point this year? Fair number of you. The rest of you, stop lying. Now, how many of you have forgotten your phone? Fair fewer. Now, our product is called the EKey, and what it serves to do is it serves to combine your keys and your phone into one device. It connects to a servo mounted to your doorway through Bluetooth from our app, and it allows you to unlock your door with a press of a button. Now, some of you might be thinking that that sounds rather insecure. And as it currently stands, you'd be right. We haven't had a chance to implement any real security features. But what we are implementing currently is a full time-stamped RSA encrypted message that is unique to your own phone and can only be sent from one particular time. So if you do not have the proper key, and if you get a key from a different time, it will no longer work 5 minutes later. So essentially, what we have currently, though we can't demo it because we don't have a monitor, keyboard, and mouse setup to run our Raspberry Pi on, but it is a Raspberry Pi hooked up to a servo motor with a custom mounting that attaches to the inside of your door frame and manipulates the deadbolt. And then we have an Android app through which you connect via Bluetooth to the lock, and you can open it.
Okay, so for the Android side of things, what we're doing right now is we're finding the Raspberry Pi via Bluetooth and pairing with the device. And then once you open the app, you're able to select the device or the lock that you want to unlock. And after selecting and connecting to that lock, that you press a button to send the encrypted key or some sort of encryption to tell the lock to unlock. So unless you have the correct encryption, you cannot unlock any of the locks that you've selected. What we want to do in the future is be able to share these locks with other people. So let's say you have a party or something like that, and you want to share the locks with the friends that only the people you want to come into your house. Then you could share that lock with those people, and you could set like a one-use only type key, so they can only open the door once, and then the rest of the times they have to call you or you have to send the lock again. So right now, as Nate said, we've only worked up to getting the communication via Bluetooth on Android and the servo, but in the future, in the next couple of weeks, we hope to add a little more UI design and add more encryption to make it obviously more safer, so people can't just open your doors randomly. Also, we have an iOS side. We also have an iOS app in development, but we ran into some problems with Bluetooth and publishing the app, and so we're working around that using an HTTP GET request. And yeah, that's it.
Hi gang, my name is Ed Karrels. I'm a new student here, just started in the PhD program. Just for a quick background, I grew up sort of in the area, a little bit north of here in southern Wisconsin. I went to Oshkosh, a state school in Wisconsin, because it was cheap, and I got a full scholarship because they didn't have hardly any National Merit Scholars there. So it wasn't the best school. A lot of my friends went to Madison. Madison is, you know, the Wisconsin equivalent of here. It's their flagship campus. But like I said, Oshkosh was cheap, and I was scared of going to a big school. This is a huge change for me. I've never been in a school this big. Oshkosh was pretty cool. I mean, it's all small classrooms. There were a few large classes like this. We call them pit classes there. I don't know if that phrase is common here. But one thing I loved about Oshkosh was that you really got to know your professors. I mean, you didn't have TAs teaching, you didn't have lots of course staff and all that stuff. You had professors directly reading your code, critiquing it, giving you a lot of feedback. And I'm not sure how that works here. I suspect you guys might miss some of that. So I encourage you, being at a big school where you're a little less connected to your core staff, try to seek out, get some of that feedback. If nothing else, talk to your friends after the assignment is due. Compare code. You know, look at each other's code and say, well, you know, I would do this better. You know, you had some good ideas here. Let me show you how I did it. I think that feedback can be pretty valuable, and you can probably even go to the TAs, schedule an appointment, and say, you know, I was wondering if you could just give me some feedback on my program and talk about this, some of the challenges I had. Now, my biggest thing I gotta recommend from when I was an undergraduate was be curious. Don't stop when the programming assignment is done. Keep going, do something interesting with it, have fun, understand how it works. You know, it seems a lot of students, I understand, you're under a lot of time pressure and you're just trying to get the darn thing working, to turn it in, and you're sick of it and too tired. And I understand it's tough, but I really encourage you to treat the course material as a starting point. You know, learning is what you make of it. Oshkosh, gotta say, it wasn't all that demanding as a computer science school, so I found it pretty easy to take it further. Now, you guys might be under a much heavier load than I was there, so you might not have the time and your I don't know, time and effort buffer to spend extra time on it, but I highly encourage you to look more into it. Be curious, see how things work, read some man pages, dig into the code. Yeah, let's see. What else about that? A bunch of my friends went to Argonne National Laboratory for a research semester thing. So Argonne is up in the Chicago suburbs, just about an hour southwest of town. And I guess there's probably a bit of collaboration between here and there. Their big thing, at least at the time, was high-performance computing, supercomputers, doing weather modeling and physics simulations and stuff. And I think they still do a lot of that, plus tons of other things. And it isn't just computers. They're a full-service science lab. One of my friends at the lab was studying the physics of cooking the perfect French fry. McDonald's hired the lab to research this to help them produce the perfect French fry. How many of you saw the movie Hunt for Red October, where the Russians developed this super secret, super quiet submarine? And the technology is based on, rather than having a spinning fan blade in back, it uses electromagnets to suck the seawater in and eject it out. So it was totally silent, and you know, all the Americans were scared. So one of the scientists at Argonne saw that movie, and he thought, I wonder if we could get that to work. So he's like, well, I happen to know we are currently storing the world's largest electromagnet. So like General Electric, I think, was going to build a new power plant, and they built the electromagnet, this huge thing, like 30 feet long and 40 feet high, but they hadn't installed it yet, so they were leasing space in one of the warehouses at Argonne. So the scientists got permission to turn the thing on and play with it. So they tried it, and sure enough, if you have a big enough electromagnet, you can suck seawater along. It wasn't strong enough to propel a submarine, but it was kind of a cool experiment. So anyway, Argonne, it was supposed to be a research semester. Take a semester off school, go, like an internship, but a full-time position for a few months during school. I loved it. The best thing about Argonne was that everyone there was a lot smarter than me. That is valuable. Make smart friends. Hang out with smart people. You'll learn a lot from them. It's kind of fun to be the smartest person in the room, but you don't grow. So hang out with smart people. Yeah, that's one of my key bits of advice. So the lowest people on the totem pole there were postdocs. They already had their PhD. They're just hanging out there trying to find a better position. So it was a great experience. I was exposed to a lot of real, how to say it, a lot of in-depth programming. They're dealing with huge system scaling issues where they have a little bit of slowdown in your code, magnify that by 1,000 processors, and suddenly your program is terrible. So they've really dug into a lot of system stuff, really got me thinking, mostly just from hearing them talk about the issues that they're dealing with in these huge parallel systems. And it just kind of exposed me to it and had that in the back of my head. So highly recommend hanging out with smart people. Now, I love the internship so much. It was supposed to be a semester. I convinced them to let me stay on for a year. I have to say I wasn't enjoying my undergraduate experience all that much, so I was kind of motivated to stay out of school a little bit longer. That year was the best thing I could have done. I kind of took a year off school, but learned a heck of a lot and made some good contacts. While I was there, we hosted a conference, and I demoed some of the work I was doing to a guy from IBM. Turns out he was the head of supercomputing at IBM, and he hit me up for an internship for the following summer. While I was at IBM, I met someone on our project left the company to go to Silicon Graphics. Silicon Graphics was super cool at the time. They had just done Jurassic Park and all the animated dinosaurs. And my boss at Argonne had recommended it. He says, "You want to intern at Silicon Graphics. They're totally cool. They're in Silicon Valley. They have beer parties every Friday, and that's where it's at." So I had that contact from the internship at IBM. So I called her and got in touch with a recruiter and got a phone screen the next day. So again, one personal link leading to another job. So I interned at Silicon Graphics the summer after that. Then I went back to school, and now after Argonne, I had a new perspective on education. I'd seen the world outside, I'd seen all this interesting stuff there was out there, and I was just a little bit more mature, and I was that much more motivated just to finish up, get out of there, and do something interesting. So the last few years just kind of sailed by. I took all my computer courses as a freshman and sophomore, pretty much finished up my major by the time I was a sophomore, and the rest of it was taking all the freshman level, biology 101 and literature 101. So that felt weird, but I had all the computer classes under my belt, so I could actually go and be productive on these internships. So internship at IBM, Silicon Graphics, that was out in Silicon Valley, California. It was great, loved it there, cool job. We were doing data mining, machine learning stuff, which is odd for a graphics company, but their justification was they had spent so much time optimizing the hardware in these machines to do high performance graphics, so lots of memory throughput and processing power, that the machines turned out to be good for data mining too, because it uses similar things, all the processing power and high memory bandwidth. So graduated, went back out to Silicon Valley for a full-time position at Silicon Graphics, and pretty much as soon as I got back out there, the company started going downhill. They were in the business of making boutique computers. So their computer was twice as fast as the next guy, and they would charge 10 times as much for it. It's a very limited lifespan business model. Yeah, they didn't survive. They were getting eaten up on the low end. Linux machines were getting faster and faster. They were confident that their machines with their custom-built MIPS processors would always be the fastest thing out there. Well, Intel just kept making faster and faster commodity processors, and they couldn't keep up. Finally, about the time that I left Silicon Graphics, they gave up. They fired their entire processor design team, sold MIPS, and started using Intel like everyone else. So that was a tough time for the company, and they were having layoffs left and right because they still had this boutique computer business model that just wasn't working because the low-end computers were getting faster and faster. Now they could have owned the graphics card market, but they're like, no, we don't like consumers. We like to sell $10,000 machines, not $40 cards. So that hurt them in the end. Their poor business ideas, and the company was just dying, laying off people left and right. Meanwhile, one of the guys in my group, he saw the writing on the wall, called up a friend of a friend, got a job at a startup down the street. As soon as he gets there, he's like, dude, quit SGI, you should come down here. We still got the beer parties. We just got $25 million in funding. It's going to be awesome. I'm like, what is it? He's like, it's a search engine that uses artificial intelligence and machine learning. I'm like, George, we work on artificial intelligence and machine learning. It doesn't actually work all that well. He's like, yeah, no, they're doing it right. It's going to be great. So he convinced me. So I had lunch with him, the founder, and it sounded like at the time they were mostly gathering really smart people. And I met a few of them, and they were all wicked smart. And that's a good sign. When you go to interview at a company, and most of the people are bozos, that company is not going to do well, especially if it's a startup. If everyone there is a rocket scientist, that's probably somewhere where you have to work. So I got hired on at Google as employee number 56. And my friend George, he was employee number 10. And I owe him the world. Everyone at Google had at least a master's degree from a top-name university. They're mostly Stanford kids, a few Berkeley, a bunch from MIT, Harvard, Yale. I'm pretty sure I was the first person there from a no-name school with just a bachelor's degree. Because I did well in the interview, and George put in a good word for me. So that brings back the point, work with smart people and let them find a better job. If you've worked with them and impressed them, they'll do the hard work of finding a job, then they'll bring you along. You know, they get a job at a successful startup, so we need more good programmers. Oh, I know this guy Ed, we gotta bring him up. So I'm lazy, I like to let my friends do the hard work of finding the better jobs, so hang out with smart people and impress your colleagues. So remember those. That's kind of my big phrase that I'd have to say, the thing I learned from my career: impress your colleagues. Don't be a jerk about it. Don't come in bragging, oh, I'm awesome. Just do good work, be reliable, be responsible. They recognize that. So at Google, I mostly worked on the advertising system. Oh, wait, I can actually start using my slides now. You've probably heard the whole thing. Luck is when opportunity meets preparation. That was what Google was for me. I mean, there were a billion startups all over Silicon Valley. There were zillions of different search engines trying to do their thing. I gotta say, I mostly got lucky, but I was prepared. That interview was tough. They basically had me design their web crawler from scratch. So what would you do? How would you build a scalable web crawler, making sure you don't crawl the same web page twice, but the set of web pages is going to be far larger than can fit in the memory of one machine. And so like, okay, well, you could hash the URL and send out to different machines, and they said, yes, but then the network latency of each message, so buffer up 100K or so of those things, and blah, blah, blah. And so it was intense. It was a lot of systems questions. I'm TAing for CS241 right now, the systems programming class right now, and Google's all about systems stuff. It was all about just understanding what's going on under the hood, because there's so many cases where things are suddenly running slowly or crashing or just hanging, and you won't understand why unless you know how it's done internally. Unless you've actually built your own memory allocator or built your own web server from scratch, you won't understand why this is going on. So most of you probably haven't taken CS 241 yet, but when you do, it's a really good class. Totally worth it. So hope you pay attention when you do take it. So system times Google. Yes, so the interview, tons of systems questions, very challenging, very interesting. This was the entire company in February of 2000. So they like to take the entire company out for a ski trip every year. The first year they took the trip, there were only 7 people at the company. This year there were 70, so factor of 10 growth over a year. There's me, barely visible, only I can tell it's me, but you know, that's how it is. As well as a few of the more famous people that have come out of Google. Oops. So yeah, it was pretty small at the time. My project was working on the ad system for the most part. I built version 0 of much of the ad system and it's replaced with much fancier stuff. And I'm pretty sure my code lives on there, here and there. I gotta say that the best part about working at Google was my email address. I had ed@google.com. That was hard to give up. I was on a bike ride one time, big organized ride, thousands of people out on the road, and I saw a guy in a TiVo jersey. I was wearing my Google bike jersey, which I thought was pretty cool, but a TiVo bike jersey was awesome. So I rode up to him, we chatted for a bit, and like, hey, I'd love to get one of those TiVo jerseys. And he's like, I'd love a Google jersey, we should meet up. And I'm all set to bust out my awesome email address. He's like, yeah, email me, I'm stu@tivo.com. I'm like, S-T-U-T. He's one letter shorter. I was blown away. So yeah, we eventually did a bike jersey swap and have a couple of TiVo jerseys. But anyway, so worked on the advertising system there, dealt with all kinds of scalability issues. You'll probably have an algorithms class where we'll talk about big N growth and why N squared algorithms are bad and log N algorithms, or ideally bold N algorithms are awesome. There's so many applications where it doesn't really matter. You know, when you're searching 10,000 lines of code, it doesn't really matter if it's O(n) or O(n) squared. It's just not that much slower. But when you launch a product on Google, the next day everyone will be using it. And if you have some crummy N squared code, things will grind to a halt, and they'll quickly blame you. So that was fun at Google, you know, really putting to use all these theoretical things we had, why it's best to do this rather than that. When it's, you know, when you actually notice a difference in performance between, say, a self-balancing tree and a hash table. By the way, the answer for almost every Google interview question at the time was, use a hash table. Because constant time lookup and all that good stuff. And when it doesn't fit on one machine, split it across multiple machines. Shard it, you like to say. Anyway, so yeah, I worked in the ad system, then eventually got stuck working on billing, and billing was really, really boring. So Google did a good job of hiring a lot of smart people, but they didn't hire many people who enjoyed working on boring stuff. So a lot of us just ended up doing boring stuff like billing, and we didn't like it all that much, because there weren't enough fun, cool projects to go around. Now, like I said, I'm lazy. I'm not that good about going and finding the new, really interesting project to work on. If you are that kind of person, Google will be awesome for you. Assuming they're the same way they are now as they were then, you could pretty much just walk in and say, I want to work on this project. I'm sick of billing stuff. And for the most part, they'll think, okay, sure, no problem. We can make that work. So, I don't know about other places, but I suspect this is applicable. You know, if you want to do something, be confident, go for it. You know, show that you're capable of handling this, and walk in. I've heard of people not even doing paid internships now, just kind of walk in and work for free for a while. I know that's kind of crazy as computer guys, because you all can get paid internships, but if you see something really awesome that you want to help out with, take it. Just go ahead and start doing it. So I didn't like billing, and I was too lazy to find something better to do. So eventually, Google went public, and I went out and bought an airplane and quit. and it was awesome. So I enjoyed biking. This is me. Went for a bike ride around Yellowstone National Park one day. So this is at the West Yellowstone Airport. Got my backpack, got my bike, got my airplane. I'm good to go. It was a lot of fun. There were a handful of us Googlers who got airplanes, and just before Google went public, we had an engineering all-hands meeting where the VP of engineering says, you know, there are engineers who started last month, and there are engineers who started 5 years ago. I understand there's going to be a large difference in personal income pretty soon. I want you to keep that out of the office as much as possible. I don't want to see Ferraris and Lamborghinis in the parking lot next week. He said, if I see a Ferrari or a Lamborghini in the parking lot, I will personally redecorate it with a baseball bat. So my friend and I bought airplanes. It's not a Ferrari, it's not a Lamborghini. So I had this whole plan on how to like taxi it in the middle of the night from the Palo Alto airport to Google through the back roads. Or claim we had an engine failure and just happened to do an emergency landing on the road next to Google. But fortunately, we sobered up and did not do that. The thing is, retirement gets kind of boring. You know, I spent a lot of time playing Warcraft. Spent a lot of time biking all over the place. I went on some cool bike rides though. You know, biked a few stages of the Tour de France one year, not competitively, just out there at my own pace. But your brain gets bored. So I started looking for new projects to do. For one, I always wanted to compute pi. You know, when I was a kid, I'd see headlines on the news, not about headlines, but they sounded like headlines to me. Somebody computed, you know, the 10 millionth digit of pi. I thought that was so cool. So I took my limited trigonometry knowledge and said, okay, if I take the arc cosine of this, I'll get pi. And great, my calculator spits out 3.141. How do I get more? And I was kind of stumped. So one day as I was, you know, sitting at home wasting time playing too much Warcraft, I thought, I should be able to figure that out at this point. So I started Googling. And it's really interesting. There's all these different formulas for computing pi, of various levels of efficiency and difficulty. You get into issues of how to do math on large numbers efficiently. Oh, we have to go on time. Like adding two numbers. That's pretty easy. It's a linear operation. It works just like the way you do addition by hand. You know, you add up the two least significant digits, possibly carry a bit, add up the next bit. So it's a simple O of n operation. But you look at multiplication, and it's an n squared operation. You multiply every digit of this guy by every digit of that guy, so it's n times n. I think in the 1960s, there was a conference somewhere in Russia, a math conference, and the guy organizing the conference, this prestigious professor from wherever, says, so during this conference, one of the things I want you to think about is the optimal multiplication algorithms. He said, currently the best known multiplication algorithms are n squared time, and nobody's been able to improve on that, so I want you all to think about how we could prove that that is the optimal way to do multiplication. Prove you cannot do it faster. So one of the students goes home that night and thinks of a better way. He figured out a way that's O of n to the 1.5 or so. And he's using a trick that Gauss figured out way back when for multiplying complex numbers. And rather than 4 multiplications for each one, you just use 3. And that was enough to change the big O time of multiplication. So the student comes to the conference the next day and says, well, actually, I just proved that you can do it faster than n squared, and here's how. And the guy running the whole thing threw a fit. He shut down the whole thing and told everyone to go home. So then he looks at the kid's algorithm and he's like, well, that's really smart. So he publishes a paper. On this better way of doing multiplication that was huge and started a whole new resurgence. And since then, people have come up with lots of other ways of doing multiplications, like with fast Fourier transforms, to the point where it's pretty much linear time. And 6 months later, the student, one of his buddies says, hey, you see that paper out on the multiplication scheme? He's like, no. Yeah, Professor so-and-so published your multiplication scheme. He put your name on the paper. That's amazing. The professor actually credited the student entirely for the algorithm. So there are cool people out there, even in the cutthroat world of academia. So this is one of the many things I was reading, all these pi computation algorithms, optimal multiplication. Oh, and just converting binary numbers to decimal. The standard way tends to be n squared, but you can actually do it with n log n if you split the thing in half. There's this cool divide and conquer algorithms for it. So I spent a lot of time doing that, and it kind of got the bug for me to go back to school. Gotta say, reading Harry Potter books was also good motivation. I mean, it's so cool. They go to school and learn how to levitate stuff or make potions that make things explode. That's awesome. So I was missing school and I was getting bored. About the same time, my wife was also getting bored and wanting to go to school, so we both got master's degrees. And that just kind of whet our appetite. They weren't very intensive programs, so we wanted to do more. We applied for PhD programs, and it was a challenge because I wanted to study computer science, my wife wants to study art history, so I had to find schools that were good for both. So it was this whole problem of the set of schools that are good for art history and the set of schools that are good for computer science and the set of schools we can get into. And the intersection of all three ended up being Santa Barbara and here. And we're kind of done with California, and there's no water there and stuff, so we came out here, where the water falls from the sky. It's incredible. We've never seen that before. So anyways, we're here. Is there any more in here? Oh yes, before I go talk about details of Pi, I want to give you a few book recommendations. I know you're probably all too busy to read right now, but over maybe Thanksgiving week or Christmas break, expand your brain, read something other than algorithms. So Chris Hadfield, he was a Canadian astronaut who got some fame doing YouTube videos from the International Space Station. He shot a music video. He recorded this video of him doing an old David Bowie song, and there was zero special effects in it. But it was amazing. It was real effects. It was him truly floating in microgravity and the Earth slowly rotating beneath him. It was amazing. So he wrote a book about his career, and what I love about it is that it's filled with tips. You know, here's what we learned in NASA, and here's how to apply it to daily life. At NASA, we practice fighting fires on mock-up space station. We've never really had a fire on the space station, but just in case, we're prepared for it. And I really like that, you know, be prepared for what might come up. I can't think of a good example right now because I'm tired, but he's got 100 cool things in the book. They're just great stories about his career and also stories about how to be successful in your career. So, fun book, totally recommend it. Confessions of Google Employee number 59. Doug Edwards was a buddy of mine. He started a week after I did. And it's mostly a collection of cool stories from the early days at Google and what it was like for him going from a standard corporate world to being at Google, where you have two kids who've never gone to business school, don't know how to manage a company, but are pretty good at it. And now Larry and Sergey, they're used to being the smartest people in the room, and when they aren't, it bugs the crap out of them. So Doug notices that, and it's a fun book. And then also Richard Feynman, interesting guy, he's got his own issues, but a lot of fun stories, and yeah, it's cool to see what the career of a Nobel Prize winning physicist is like. So I wanted to talk a bit about my Pi project. First of all, clarification, I didn't actually compute that many digits of pi. I computed a handful of digits really, really far out. So it's an easier pi record to compute. Computing digits from 3.141 to some point, that one, the furthest that's been computed is, I think, 12 trillion places. And interestingly, all the computations of that type used to be done on supercomputers, but the algorithms have progressed faster than the hardware, and now all the leading computations have been done on PCs. They don't even need supercomputers anymore. And they're pretty much limited by how many disks can you hook up to a system and how fast can you get data in and out of the disk, because the algorithms are so fast that they're not really CPU bound anymore. So I did a different computation where we target a digit really far out and just compute a few digits from there. So the previous record was the 500 trillionth digit, set by a team at Yahoo. They took a Hadoop cluster and basically showing off how Hadoop works. They put 1,000 8-core machines working on this for about a month and computed the 500 trillionth digit of pi. I did the same thing on one machine with 4 GPUs, also in about a month. So that was my key innovation, using GPUs for the process, because it's very parallelizable. We're just doing a huge summation. So let me switch to my pi slides here. Yeah. So there's lots of different formulas for pi. Do I have a few more here? Oh yeah. Just in case. Here are a few formulas for pi. There we go. Kind of getting chopped off. So here are a few different formulas for computing pi. From some pretty simple ones up top. Arctangent. In Calc 2, you probably have been or will be exposed to some formulas for pi based on arctangent. Interestingly, the one on the left, this guy, pretty simple, and it's just arctangent of 1. But if you plug in some other numbers, where there's a larger number in the denominator, since that number is being multiplied by all these powers, the numbers get smaller faster, so it converges much faster. I forget the exact thing, but this one, the one on the left, converges pretty darn slowly, but the one on the right converges extremely quickly, and up to about 1990, the one on the right was the leading way for computing digits of pi. The one on the bottom, which is chopped off here, and on the side ones you can see it, called the Chodnovsky formula. It's a monster. You can see all the factorials and stuff in there. That is currently the best known formula for computing lots of digits of pi. If you plug in just the first term of that summation, it computes pi accurate to, I think, 15 digits. And each additional term computes about another 13 to 15 digits. It's huge. And to do it efficiently, you have to do a lot of greatest common denominator calculations and just be very clever about keeping the numbers as small as possible. But that's the method that everyone uses for doing lots of digits. Yeah, so I'm just kind of showing what this looks like. You've got this big summation and it's converging, so the digits get closer and closer to pi, and they get smaller and smaller. Yeah, so my calculations, I computed the nth digit. So you kind of start by saying, I want to compute the 1,000,000th digit. So I'm going to take this whole formula and multiply it by 10 to the millionth power, effectively shifting it a million places to the right. Now, I had to do all my calculations in base 16 because this formula here that I used, see that 1/16 to the kth power? That cancels out with a digit shift. So I said I want to shift the digits a million places to the right. In hexadecimal, I would multiply by a power of 16. So I'll multiply this whole thing by 16 to the millionth power, which is going to cancel out with that guy and make the formula much easier. If you did 10 to the zillionth power, it wouldn't really cancel out and you can't really do the same calculation. It would still sort of work, but you don't get that great efficiency you get in base 16. So scientists are still, or I should say mathematicians, are still looking for a similar formula that lets you easily extract digits of pi in base 10, but nobody's found one yet. They have proved that there is no such formula in this structure, but there might be one out there someday. And this is pretty active research. This was discovered in, I think, 1995. So, yeah, basically the upshot is you can compute the nth digit of pi with constant size memory, and it runs in big O of n time. So if you want the millionth digit of pi, do about 1,000,000 iterations. And how it works, you basically do a bunch of algebra and boil it down to a formula like this. 2 to the p modulo m divided by m. So the inner loop in my program is this. I compute P and M, they're a simple function of K, the iteration number that you're on. Do one modular exponentiation thing, so I raise 2 to the pth power modulo M, and then divide T by M and add the results. So pretty simple, but you're doing lots of iterations, about 1 iteration for each decimal place or each hexadecimal place that you want to go to. So my last run, I did the 10 quadrillionth digit, so I had to do about 10 quadrillion iterations of this. So is that a million? Anyway, a lot. But it's easily parallelizable because you're simply adding all these terms together. So I would allocate work units of about 1 billion terms to each GPU and say, all right, you go and compute these billion terms, then assign the next GPU the next billion terms, and just add up the results. That billion terms takes about a minute to process. So I would have one master machine allocating these work chunks, and then I would start up client processes on every machine I could get access to. And pointing at the master, they would request jobs, compute it, send the result back. So pretty much every computer on my campus at Santa Clara University had a GPU. So for the ones that I could access remotely, the Linux ones, I would have my program running in the background all the time. And whenever a student logged off, my program would go to work and put the machine to use. Now when they logged on, I had to quickly pause my program because I'm using the GPU. And if you're actually sitting at the machine trying to use it, and you've got someone like me beating up the GPU, the graphics performance is terrible, and nobody wants to use the machine. So I demoed this technique to the sysadmins, and they grudgingly gave me permission to leave my program running all day. I basically had to prove it worked by accidentally letting it run all day in a few machines, and said, oh, oops, hey, nobody complained, it must be okay, right? So I call it Gorilla Supercomputing. Gorilla like G-U-E, not G-O-I. Anyway. So yeah, so that was my program. Spent a lot of time optimizing those routines. Had to write most of the low-level stuff in the assembly language for the graphics cards, which is integrated really well in the system. It wasn't all that painful. Let's see, yeah, most of it was implementing large integer types. I implemented 128-bit, 192-bit integers. Blah, blah, blah. Oh, there's a cool math formula I could use called Montgomery reduction. So that mod pow routine, modular exponentiation, a modulo operation is pretty much just as hard as a division operation. And they're both pretty hard. The addition, subtraction, multiplication instructions on most processors is pretty darn fast. Maybe 1 cycle, maybe 2 cycles. But division tends to be really slow. And particularly on the NVIDIA graphics cards I was using, they don't even have a division instruction. They have a single precision float reciprocal instruction. So if you're just doing single precision floats, you do the reciprocal of one number and then multiply by the other, and then get your division. If you want to do, say, a 32-bit integer division, that floating point number has less precision. So to actually start by doing a floating point division and then do a few rounds of approximations to make it more accurate, you might run across Newton-Raphson approximations in your classes, and that's what it uses. So the compiler actually emits about 17 instructions to do one 32-bit integer division. If you do 64-bit division, it's about 70 instructions worth. So it was painfully slow. So I was doing everything I could to optimize that modulo thing. A really cool trick I ran across was called Montgomery reduction, where it lets you temporarily change the base of the modulo operation. So say I'm doing 100 modulo operations and they're all modulo 53. Well, 53 is a really awkward number to work with. So with Montgomery, you do a little operation, change your numbers in a way that now you use modulo 64 as your base. So rather than doing modulo 53 a whole bunch of times, you do modulo 64 a whole bunch of times. Why is that easy? Question for the audience. Why is modulo 64 easy? Say again? Overflow? No, it's not related to overflow. Yeah. Yeah, it's the lowest few bits. So say 64, that's 2 to the 6th. So you only need the lower, to just strip off the lower 6 bits to get your modulo. So you can turn that really slow division operation into 1 bit mask operation, which is fast on everything. So I implemented that for everything and got about a 7x speed up just from changing those modulo things. And I found that just with a lot of Googling, that was the slowest part of my program. So I spent weeks searching through books and papers and web pages for high performance modular exponentiation algorithms, and finally found that one in the back of some book about computing prime numbers. And yeah, it was a huge win for my program. So to put it in hard numbers, so that was a 7x speed up, and I think 7x overall program performance, not just for that one routine. The one routine was probably like 15x faster. But on my last computation, it took about 3 months to run. So without that optimization, it would have taken nearly 2 years to run. So it's a huge deal. One day with a little better buffering, I changed my GPU usage from 97% of the time to 99.5% of the time. And it sounds like nothing, 97 to 99.5. But that shaved like 4 days off of my computation. To put that into dollars, my first run, I was doing it all at home. And my machine, let's see, it used a lot of power. So this is the computer I did the work on. Those are all GTX 690 cards. So internally, there are 2 GTX 680s running a little bit slower. But so to the software, it looks like 8 GPUs in this thing. So I'm busy keeping all of those cards busy. Idle, this machine draws about 260 watts. When all the GPUs are running, it draws about 1100 watts. This is what the temperatures look like on the cards when I start my job. So they idle at about 60 degrees Celsius. So that's already kind of hot. As soon as I start my program, they get close to the boiling point. And you hear all the fans spin up. All the fans are at like 95% of their rated speed. So yeah, it uses it hard. I actually fried a power strip. The strip says it's rated for 1600 watts, but after running for about a month, actually a few months at this point, it melted it, drawing only 11 watts. So I left Belkin with a bad review on Amazon. Don't buy the cards where the plugs rotate. They're not properly engineered. Tip for y'all. So anyway, so I did this run on my at home. I started it in July in the living room, but it's July, and this thing is basically an 1100 watt space heater. So I moved out to the garage because it was just ridiculous. So if you look, you can see like my bicycle wheel behind it. That's my water heater. So yeah, it was banished outside, and with the cost of electricity in my neighborhood, it cost about $25 a day. So optimizing my code, just adding another little buffer for the job queue to take it from 97% efficiency to 99.5% efficiency, shaved off 4 days. So that was $100 I saved right there. I know, it's not that big a deal in the long run, but I thought it was cool. Let's see, anything else interesting here? Oh yeah, so you do all these calculations, and you get a bunch of digits that look like random noise. Like, how do I know these are actually accurate? Because nobody else had ever computed these before. What you do is you run the whole calculation again, offset by a digit or a few digits. So all of the math routines are going to be using different numbers. They'll be exercising slightly different parts of your code. And if at the end of all that, everything matches up, just offset, you're good to go. So here's what it looks like with 2 different runs, a couple digits off from each other. And so here you can see it matched up nicely. But you notice that the last 7 digits were wrong. That's round off error. Did my best to minimize it, but since on every iteration of that loop there's a division operation, with the division, the last bit could go either way, since it always has to round that last bit, since it's all integer math. So you get about up to 1 bit of error with each iteration. So, and yeah, so there's always a little bit of inaccuracy, but that's how you double check your runs. And I talked about how I allocated the work units in like 1 minute at a time. I would give it 1 billion terms to compute. I would save all those intermediate results. And if at the end those numbers don't match up, I can go through and check all those intermediate results and see, oh, you know, this guy from 304 billion to 305 billion, one of the GPUs who did the work had an error. So I would redo that calculation, get the correct answer, paste it in, patch up the data until it all works. And it was interesting, I actually found a few cards that threw off about an error a day, but just the older cards, GTX 570s, most of the cards were fine, but a few of them would throw off a few errors. It was pretty consistent, there's just a few cards that were bad. So I asked the sysadmin, if and when you upgrade those cards, I want the bad ones. I want to play with those, because I was never able to reproduce any of these bugs. It was consistently on the same machines, but whenever I redid that exact same calculation, it always came out right. So I figure it's just a matter of doing it more often to try and trigger that bug. But as far as I can tell, it was not a bug in my software because it was only on those few machines. So I know it's easy to blame the hardware, but I'm pretty sure it was the hardware. Let's see, anything else interesting here? Let's see. Yeah, so in reality, no calculation ever needs more than 38 digits of pi. That's already an obscene accuracy. So computing more than 38 digits of pi is just kind of a fun exercise in computer engineering. And it was a fun project. I mean, I was dealing with everything from doing modular exponentiation efficiently to finding a power strip that won't burn out. So it was a lot of fun. Plus, I think it looked really good on my grad school applications. I was able to say, I have computed the most or the least significant digit of pi ever computed. Oh, and one more thing. I told you how I'm lazy about finding better jobs. I want my friends to find me better jobs. When I was at Argonne, there's all these wicked smart researchers there. By the time I was applying for grad school, they were all department chairs all over the Midwest. So the guy I rented a room from, he was the chair of the computer science department at Madison. Let's see, Ian Foster had beers with him a few times, nice guy. He's like the head of parallel computing at University of Chicago. And Bill Grob, I kind of reported to him and the guy Rusty Lusk at the same time. They were two of the three people who, I'm sure it's a huge group, but their names are on the book. Two of the three people who pretty much created MPI, which is the system that everyone uses to do supercomputing now. And Bill Grob, he's on the faculty here. I sent him an email, it's like, Ed, good to hear from you. Yeah, come on down to Illinois. So let your friends find better jobs and they'll bring you along. So Bill Grob got me in here, and that was great. I look forward to working with him more. Let's see if there's anything else I had. That's about it. Any questions? Yeah. How do I check if I'm right? Sorry, it's Nick. With the pi computation? Yeah, that's where I was saying you do the same calculation 1 digit off. So the top line is one run, and the next line is another run, where I basically do all the work again with slightly different numbers and make sure it matches up. For lower precision stuff, some other people who have computed digits of pi have published their results, like here are the first 100 digits starting at the 1 millionth place or the 10 millionth place. So I could compare with those during testing. But for the other stuff, I had to rely on checking my own work. Any other questions? Yeah. Let's see. So they went public, I think it's September. I stopped working in December, so about 2 months, and then I officially quit the next June. I took some time off just to see what it was like, and it was awesome. I loved it. So I took my boss out for what we call a $100 hamburger. It's when you fly to an airport with a diner and you get a $5 burger, but you spend $95 in aviation gas. So it's a $100 burger, so I took him out for a $100 burger. And he's like, you seem to be really enjoying not working. Should we schedule an exit interview? I said, yeah. Yeah.
Why'd you pick NVIDIA graphics cards over AMD?
Why NVIDIA over AMD? Mostly the programming tools for NVIDIA seemed much more complete. They had better debuggers and stuff. When I first started out, I don't think AMD even had a debugger. NVIDIA is good about publishing assembly code you can use for it. AMD, their tool precision performance is much better than the consumer level cards than NVIDIA. But I wasn't actually using doubles. I was doing everything with hints, and I just wasn't able to get similar performance out of AMD. If I was using doubles, AMD would be great, but yeah, I was able to get better performance for integer stuff out of NVIDIA. Yeah. I don't know. Maybe teach, maybe just get a lab at a research center. There's a high performance computing center on Maui, so that would be kind of fun. Except it's technically a Navy facility, and I don't really want to report to a colonel. That sounds kind of crummy. But frankly, I think my wife is going to have a harder time finding a position. She wants to be a curator in art research. So I can be pretty happy pretty much anywhere. So I've promised her once we get our PhDs, I'll let you choose where we're going to move, and I'll just tag along and keep myself busy. Any other questions? Yeah. Am I going to TA anything? I hope not. It's a lot of work, and parts of it are enjoyable, but I gotta get to my research. Yeah. Say again? Oh, I want to do parallel computing. There's a bunch of interesting stuff in NPI that just isn't as efficient as it should be. It's interesting. Supercomputing, the hardware is there. It can do anything. There's some software to make it all work if you're willing to work really hard on writing it. But a lot of these scientific programming people, their specialty is climate models. They're not expert programmers. So you'll have a lot of programs that are, sure, they're running on big, huge machines, but they didn't really spend a lot of time writing good code. So one of the issues they're having is they don't use the parallel I/O efficiently. The Blue Waters has something like 1,000 hard drives, and you can stream data in and out of them in parallel, all of them at the same time. It's supposed to have like 1 terabyte per second total bandwidth. So they looked at how much I/O programs were actually using, and they said 60% of the jobs running on that machine and a couple other supercomputers they monitored, 60% of all the programs wouldn't notice if you just used a thumb drive, a consumer level thumb drive. They just weren't using this massive I/O throughput we had. There's a 2-week job, he said, that would spend 5 days loading all its data, compute for 4 days, and then another 5 days to write it all out. Like, if you just use the I/O system efficiently, you cut a 14-day job into a 4.5-day job. And so I think the big thing in supercomputing is to make the system easier to use. So there's a lot of work to do there. Any other questions? All right, best of luck. Oh, and one last thing. If and when you do take CS241, I'm very happy we have a MapReduce project, a Karel programming thing, where you can plug in different algorithms, and I just implemented my high computation stuff as a MapReduce program, so you can run your own jobs computing pi. It doesn't use the GPU, and it is not really optimized, but it's still pretty cool. You can compute the millionth digit of pi in less than a second. So, all right.
Class is over. Oh, wait. we have one thing to show you guys from the VR and CV lectures. It's gonna take like 1 minute.
I couldn't finish one question. If you have a DAG, and then how you find healthcare.
Feel free to start packing up and all that. Quick, but I showed you a few photos of the reconstruction of R2-4. I actually got the model now, so you can see it in all its glory. That's not pleasant.
What I did was
right.
essentially I did the same thing that
then you can play around with.
But you run it just once. What do you keep a track of is you can find
orientation, all that.
That work either like only in the reverse.
Okay.
Only the
There. That was the VGA. You want to take this?
But how can you keep track of every single one?
No, as soon as you hit it, as soon as you hit it, you know.
Hey, I can show you guys how to data center hackerspace tomorrow. This took 3 hours. It's like,
as soon as you hit like a reverse,
this version of it is like 200
then you search for another reverse.
The original is like 2 gigs. Not quite the amount of data that is used to dealing with. That's significantly smaller. But this is what a lot of random data can sometimes look like.
Yeah, but
essentially, what it's doing in its essence is looking for all sources and all. Two sources cannot be.
well, no. So the thing is, like, okay. So if you have a source, wait, okay, that's not.
I mean, two sources can't reach each other.
Yeah. Oh.
Two sources can never reach each other. Two
So you
things
just
can never
find
reach each
all
other.
the sources. Well, okay. What about the graph? Okay, so you have a node.
You find all sources. You find all sinks. Two sources can't reach each other. Two sinks.
No, but like there's more than just that.
No, and then you run it from one of the sources. If like neither of those things get satisfied, then you run the algorithm from one of the sources, and then you graphing. But no, I don't know. I didn't say that.
No, I was thinking. Okay, so if you have a graph, say okay, DHE source sync.
Yeah.
Then you have like 2 trees essentially, and then they reach here. How do you know that these 2 are not connected?
If these 2
are not.
Wait, draw out what you're saying. Here.
You're at 374.
Yeah.
Is it like so? It's algorithms. Is it basically like algorithms based on trees?
There's a lot of graphs.
Graphs and like dynamic.
So those were the 2 big things you covered so far.
Oh gosh. Yeah.
I mean, algorithms. Like there's also models of computation.
Yeah.
Like, you do like languages.
Languages.